Ever get that feeling like when you're using your computer that it's pulling off some kind of magic trick? Yeah. Like, how can it be juggling a dozen apps all seemingly at the same time? Today, we're going on a deep dive to uncover the secrets behind this illusion using the Xinu operating system as our guide.
Okay.
We've got excerpts from the second edition of the Xinu design document, a rare Japanese translation, no less.
Wow.
To help us unpack some really fascinating concepts.
It all starts with understanding that what we perceive as like simultaneous execution is actually a clever illusion orchestrated by the operating system.
So it's not that I actually have multiple things happening at the exact same like nanosecond. My computer's is really good at switching between tasks.
Precisely. Most systems, especially those in simpler devices or with stringent safety needs, use a straightforward approach. Synchronous event loops.
Oh.
Think about your TV remote.
Right,
It responds to button presses one at a time.
Makes sense.
But for more complex systems like Xinu, multitasking, or multi-programming is the name of the game.
Multitasking. Okay, yeah, that rings a bell. But walk me through it. Like, I'm just starting out with OS design.
Okay, so picture the OS as a conductor.
Yeah.
Gracefully cueing different sections of an orchestra.
Got it.
Each instrument gets its turn to play.
Okay.
And the conductor ensures a harmonious blend, even though they're not all playing at once.
So each program, like an instrument, gets a slice of the processor's time. But how does Xinu prevent these programs from tripping over each other when they all need access to the same resources? Let's say two programs both want to use the printer or try to modify the same piece of data. That sounds like a recipe for disaster.
And that's where the concept of a process comes in. In Xinu, each program runs within its own isolated process, like a chef with their own dedicated workstation in a bustling kitchen.
So it's not just the code running in isolation, it gets its own little world of data and resources too.
Absolutely. Xinu dynamically creates, manages, and even terminates these processes, making sure each one has what it needs to function without interfering with others. Now you might be thinking, so a process is just like a function, right?
Yeah, that's kind of what I was picturing in my head.
Well, there's a key distinction to keep in mind. In the world of concurrent programming, where multiple things are happening in like overlapping time frames, things like variables or the stack associated with a piece of code are tied to the process, not the code itself. This ensures that each process remains independent and avoids conflicts, even if they happen to be running the same piece of code.
Yeah. Okay, so I'm starting to get how Xinu creates these isolated processes, each with their own little set of resources.
Right.
But what happens when they need to interact, especially when sharing resources? It's like those moments in a kitchen when two chefs need to use the same oven at the same time.
Yeah.
Things could get a little heated.
That's a great analogy. And you've hit on a critical aspect of operating system design, synchronization.
Okay.
Without it, you're right, things would descend into chaos pretty quickly.
So how does Xinu handle this? I'm imagining some kind of system for, making sure processes cooperate and don't step on each other's toes.
You're exactly right. Xinu employs a mechanism called semaphores. They act like traffic signals, ensuring smooth and orderly access to shared resources.
Semaphores? I've heard the term before, but honestly, it's always been a bit fuzzy for me.
Think of it this way. Imagine a single-lane bridge.
Okay.
Only one car can cross safely at a time.
Right.
A semaphore acts like the traffic lights on either side, ensuring only one process accesses that shared resource, our metaphorical bridge, at any given moment.
So it's about preventing those race conditions we talked about earlier, where like multiple processes trying to access or change the same data simultaneously could lead to unpredictable results.
Exactly. Semaphores are all about achieving mutual exclusion. This ensures access to shared resources is exclusive, preventing those race conditions and maintaining data integrity. In the Xinu design document, there's a great example of how a counting semaphore is used to manage access to the system's only printer. Only one process can hold the printer semaphore at a time, guaranteeing that print jobs are executed one after the other without interference.
That's a really clear example. So if I'm reading the design document correctly, it looks like Xinu uses what are called counting semaphores. What makes them different? Are they just a more complex traffic light system?
You're on the right track. Counting semaphores are like traffic lights, but instead of just red and green, they have a whole range of numbers they can signal. This means they can manage more than just exclusive access. They can control how many processes can access a resource concurrently.
Okay, that's interesting. So it's not just one or none, but like potentially two, three, or, any number of processes accessing a resource.
Exactly. Think of trying to download multiple files simultaneously.
Right.
A counting semaphore could limit these downloads, preventing your network connection from getting bogged down. In Xinu, this type of control is essential for managing things like the number of processes that can access the disk at the same time.
This is making a lot of sense. But if you've got multiple processes all kind of waiting on a semaphore, does Xinu treat them all equally? Or is there like some kind of priority system?
You're anticipating the next layer of complexity. Xinu does prioritize processes waiting on a semaphore, and this is where scheduling comes into play. It's another fascinating aspect of operating system design.
Scheduling. I'm all ears. This is where we delve even deeper into the inner workings of Xinu, right? Okay, so we've covered a lot of ground here. We've talked about how Xinu creates these isolated processes, each with its own set of resources, and how it uses semaphores to manage their interactions, especially when sharing is involved. But there's still this one big question lingering in my mind. How does the OS actually jump between all these different processes happening seemingly simultaneously?
That jumping is called context switching, and it's the heart of multitasking. It's the mechanism that allows the OS to, seamlessly transition from one process to another, making it seem like they're all running in perfect harmony.
Context switching. That sounds incredibly complex. Can you break down what's actually happening during this process?
Absolutely. Let's go back to those chefs in the kitchen. Imagine one chef is in the middle of preparing a delicate sauce, carefully measuring ingredients and, monitoring the heat.
Okay.
Suddenly, the head chef needs them to switch gears and start prepping vegetables for another dish.
So to switch tasks effectively, you can't just have the chef drop everything and move on. You need to preserve the state of their current task, right?
Exactly. You need to make sure they can pick up right where they left off with the sauce once they're done prepping the veggies. In the same way, context switching involves saving the current state of a process before switching to a different one.
So what does saving the state of a process actually entail?
It means meticulously recording every essential detail of the process's current execution environment. We're talking about the values stored in the processor's registers, the exact point the program has reached in its execution, and even information about the process's stack, like local variables and function calls. This entire snapshot of the process's state is stored in a special data structure called a process control block, or PCB for short.
The PCB, that sounds familiar. Is that described in the Xinu design document?
It is. The design document actually goes into quite a bit of detail about the structure of the PCB in Xinu. It's fascinating to see how they've organized all the crucial information the OS needs to manage each process.
So when a process needs to be paused, its state is saved into its PCB. Then to resume that process, the OS simply reloads the state from its PCB and it picks up exactly where it left off.
You've got it. It's like taking a detailed photograph of the chef's workstation, including the position of every ingredient and utensil, and then using that photograph to perfectly recreate the scene later on.
That's incredible. But if this context switching is happening constantly, as you say it does in multitasking systems, doesn't that create a lot of overhead? Saving and restoring all that information must take some time.
That's an excellent point. Context switching does introduce some overhead. The efficiency of this process often depends on the processor's architecture. Some processors have features designed to speed up context switching, but it's always a balancing act for OS designers. They need to weigh the responsiveness of multitasking against the potential performance impact.
It sounds like there's a whole hidden world of optimization and trade-offs happening behind the scenes that most of us never even consider when we're, browsing the web or running applications.
Absolutely. And that's just scratching the surface. There's so much more to operating system design than what we've covered today. We haven't even touched on memory management, file systems, device drivers.
It sounds like we'll need to save those topics for future deep dives. But before we wrap up today's deep dive, I want to circle back to something you mentioned earlier, scheduling. You said Xinu prioritizes processes waiting on a semaphore. How did that factor into all of this?
Yes. Scheduling is the OS's way of deciding which process gets to use the processor at any given time. Xinu uses a priority-based scheduling system, which means that processes with higher priority are given preference. However, as you can imagine, this can lead to situations where low-priority processes might end up waiting indefinitely for their turn if higher-priority processes are constantly demanding the processor's attention.
That makes sense. So how do you balance the need to prioritize certain tasks with ensuring that all processes eventually get a chance to run? It seems like a tricky problem to solve.
It is a tricky problem, and there's no single right answer. Different operating systems use different scheduling algorithms to strike that balance. Some prioritize fairness, ensuring that all processes get a fair share of processor time, even if it means slightly slower overall performance. Others prioritize responsiveness, giving preference to interactive tasks like user input to make the system feel snappier. Xinu, as described in the design document, seems to lean towards prioritizing real-time responsiveness, which is essential for embedded systems where tasks often have strict timing requirements.
So there's no one-size-fits-all solution, just different approaches with their own strengths and weaknesses, all aimed at making the most efficient use of the processor's time.
Precisely.
Well, I have to say, this deep dive into Xinu has been truly eye-opening. It's incredible to think about all the intricate mechanisms happening behind the scenes to create the seamless computing experience we often take for granted.
I agree. It's a testament to the ingenuity of operating system designers.
For our listeners who are eager to learn more, we encourage you to seek out the Xinu design document. Even if you don't read Japanese, there are resources out there to help you explore the fascinating world of operating system design. Until next time, happy coding.